It's my great pleasure to introduce Raf. And I've known him since 1998, for many, many years, within Robot Soccer and RoboCup. He's a big champion of Robot Soccer. He ended up coming in '98 to Paris to RoboCup and asking me, having this very naive conversation with me, so what is this all about, and so forth. And I was explaining to him. He came in '99 and he won. He beat everyone. And since then he won several other times, and he was a very strong presence at RoboCup, introducing literally the speed, the control of robots before. We can say before Cornell or before RAF, RoboCup was something. After RAF, RoboCup was something else. So it's before and after. And RAF was a professor at Cornell. He did RoboCup having teams of undergrad students working on the complete project, from building the robots to actually all the control. And he's now a professor of dynamic systems and control at ETH. So he left Cornell and is now Switzerland. In the meantime, he created a company very successful. And it's a great pleasure and a great honor to welcome you to Carnegie Mellon. Thank you. Thanks.
Okay, so what I'm going to speak today is very anecdotal. I'm not going to have a lot of equations. It's really kind of a personal journey that I've gone through about how I want to structure my research environment in Switzerland. And it's pretty much what I said in the talk. So I really want to address 3 points. The first is, I think lack of robustness is one of robotics' Achilles' heels. That is really, I think, what's holding back a lot of potential deployments of robotic systems. And I think in an academic environment, it is difficult to motivate robustness. They're just not the incentives. You know, a lot of the incentives are lined up in creating new capabilities, demonstrating that you've created a new algorithm. But you know, nobody knows if it took 3 weeks to set the parameters for your algorithm to make it work the way that you presented in the paper. There just isn't that scrutiny that's paid to those aspects of our research. Not only at the how generalizable algorithms are, but also the hardware itself. When mechanisms are designed, when you see great videos on the web, you don't know if it took a month to create that video, right? So there's just not a lot of incentives to have robustness in a research environment. So how do we do that? Because it's important to have robustness, right? A lot of students here, you're going to go out and you're going to do great things, become professors, start companies, et cetera. I think a key requirement is to have a robust system. So we impose it indirectly. So I try to set up an environment where we impose robustness indirectly, and we do that via these 3 things. We try to have demos. When you come and visit our lab in Switzerland, you can go to any of our labs, and within 5 minutes, we can give you a demo of any of our projects. And this is something that the culture that we instill in our group. The other one is more historical competitions. I think a lot of people here are involved or have been involved in competitions. It's a great way to motivate coming up with a robust system. When you're competing against other people, if it doesn't work, it's a lot of egg in the face. And the other one is live performances. We also do, our group and me personally have done a lot of live performances at exhibitions, art galleries, et cetera. And I'm going to talk a little bit about that. Okay, so as I said, this is going to be a very anecdotal talk, and I kind of want to guide you through how I got to this way of thinking about things. So I'm actually going to start way back when I was an undergrad at the University of Toronto. We had this second-year design project, which was kind of a lot of the reasons why people went into engineering was because of the second-year design project. It had this very, this huge aura around it. When you're a first-year student, you hear about what the second-year design project was, what the people were attempting, and it's like, I can't wait until I get to second year so I can do this. So our project in that second year, was 4 of us, was to build a voice-controlled robotic crane. Now, this was back in '86, '87. Now you're saying, well, what's so hard about? I could probably do that with Lego Mindstorms, right? But back then, it was a big deal, right? This was the era of the Commodore 64. And so that was the computing platform. And the project, again, was 4 of us. And one person was responsible for the mechanical design. One person was responsible for the electrical interface. Third person was supposed to design the computing platform from scratch based on the 6502 microprocessor, which happened to be the same as what was on the Commodore 64. And the 4th person, which was me, I was supposed to architect the system and write all the algorithms. So year-long project. The mechanical, electrical guys were doing a great job. We were doing a lot of testing, system integration. The computing platform was this guy that was known as kind of this whiz kid, and he always kept on telling us that he had everything under control, and we believed him. So basically, it came to 2 weeks before the end of the year when we were supposed to display our project, and you know, we realized that he basically had not delivered what he was supposed to do. He did not have a working computer, and there was no way that what he had was going to work anytime soon. So we scrambled. We all pooled our resources to try to make a computer from scratch. In that 1 week, we couldn't. So we were panicking a little bit until we realized that the 6502 microprocessor that was supposed to run the algorithms on the computer was the same one as the Commodore 64. So we thought, why don't we use the Commodore 64 to run the algorithms, hook it up to the electrical part and the voice-controlled robotic crane. So 3 days before the project was due, I had to basically type in all the code in assembly that I had written into the computer. So we had these 3 pages of hex codes that I had to type into the computer, and I got my girlfriend to spend 8-10 hours with me to read all these things, and then we had to spend another 3 hours rereading them to make sure that we had typed everything correctly. It was really late at night. We got up the next morning, typed run on the computer, disconnected the keyboard. We actually had it cut, and then we connected, because it was the same input-output interface, connected the electronics, and I'm not lying to you when I tell you this, it worked the first time. I know it sounds unbelievable, but the reason it worked the first time is because the algorithm was actually very simple, and that's something that kind of one of the lessons learned in part of the story. So it was great success. This thing worked. You know, it only had to recognize 8 words, so you can imagine the algorithm didn't have to be that complicated in order to do this. So kind of what were the lessons learned in doing something like this? Kind of really had a lot of influence in what I did afterwards. First is, what is the simplest algorithm that does the job? Other students, other groups were trying to do voice-controlled mechatronic systems, you know, and they were reading research papers on how that could be done. This was back in '86. You know, I was a very lazy student. You know, I was not going to read research papers as a second-year undergraduate student. I just thought, I got to recognize 8 words. What's the best way to do it? And you know, stumbled onto this idea of just counting 0 crossings and making a pseudo spectrum of my voice. And in fact, I got very good at training the algorithm, training myself so that the algorithm would be able to recognize left versus right by saying one differently than the other. So that was good enough to get the job done. So that was an important lesson that I learned. Second one was integration. It's extremely important. We did a great job at integration with the mechanical, electrical, and the system level aspects, but the computer, we did not. We were fortunate that we were able to get around it. That was an important lesson. And the third is the team, right? Whenever you do any sort of robotic projects, and like many of you are involved, you got to make sure you have a really good team. And in fact, that's probably, I should have put that first, right? You need to have a good team in order to deliver something. So that was the lessons learned, and there was another lesson that I learned, and that was that if I can find someone that is willing to spend 10 hours with me reading hex codes, then that somebody's very special, so I ended up marrying her. So she's my wife, and we're happily married. Okay, so that was an important lesson I learned as an undergrad. Then I'll skip grad school. There's a lot of cool things there that I learned about robustness, but I'll jump right to RoboCup. And you guys know a lot about RoboCup, so I'm not going to spend too much time. So RoboCup is something that we competed in from 1999 to 2005. You've seen videos like these from Manuela. In fact, the robots look very, very similar. By that time, the robots tended to be pretty similar. What the algorithms were really, people started to differentiate themselves from that time on. Systems are quite capable. It's a great competition. We had, as Manuela said, we had about 30 students working on this project, undergrads, graduate students, postdocs some years, and myself learned a heck of a lot from doing it. One of the things that really allowed us to do well in the competition was this hierarchical modular system that we designed. So the key idea here is actually quite simple. We have these nonlinear dynamics of the system, and there's a lot of friction and backlash, et cetera, what you can do is you can design a low-level controller, wrap it around here, so that the system actually looks like a much simpler dynamical system. So design your local controller to make the dynamics look simpler. Not trivial, but simpler. These are still, they're both simple and they're both complicated at the same time. They're complicated in the sense that you have to worry about differential equations, but we have techniques for coping with that. So that allowed us to do very high performance motion planning. We could do things like 60 times a second for multiple robots, explore tons of trajectories. So we could explore thousands, if not millions, of possible trajectories, and that is how we made our high-level decisions. We would explore what-if scenarios, and we had these very good motion primitives that would allow us to abstract out the dynamics of the system. So what were some of the important things that we learned doing RoboCup? The first is maintainability, flexibility, and reconfigurability. I think one of the reasons why we were successful is that we had a very robust mechanical system, but we also had a very flexible and reconfigurable system. It's only now that at the competition you can actually learn from, the system can learn how to play a better game of soccer. Back then when we were competing it was very difficult to develop algorithms. You just didn't also have the data where you could learn about your opponent in real time. So what do? We used to scout the opponents before the games, and we had a system that was very reconfigurable. We could very quickly change its attributes so that when we played a team, we would be able to take advantage of their weaknesses. So that was an important thing about that we learned from RoboCup. And related to that is you're really as strong as your weakest link. One of the nice things about doing competitions such as RoboCup is that it's not that you have a tool and you're looking for an application of your tool. You're really trying to solve a problem. You're trying to win this game of robot soccer, right? And there's all these various things that go into doing that, not just algorithmic and not just engineering-wise, but also project management, et cetera. And you're really as strong as your weakest link. So you end up discovering what is really important by doing competitions. You discover what is robust, what is fragile. So that was a very important lesson that we learned. And the third lesson is that wireless is really unreliable. Okay? So in fact, that's really guided a lot of the kind of work that I've done where I do wireless. You always got to bake it into your head is that never close loops on wireless if you're expecting a certain level of performance. You have to architect your system realizing that wireless can be completely unreliable. So another project that I got involved in is called the Robotic Chair, and this is going to lead more into these public performances. It's a collaboration with Canadian artists Max Dean and Matt Donovan. It's a chair that falls apart into 6 pieces and then proceeds to reassemble itself. And it does this thousands and thousands of times, so you can imagine that the platform itself has to be quite robust. It's appeared in many venues. It's a limited edition of 6. 2 have been sold, one to the National Gallery of Canada and one to a private collector in London. And these are some of the pictures from these live performances. But what I want to show you this picture, this is a little short video, is when we first displayed the Robotic Chair live in 2006, and it was at a venue called Idea City, which is the Canadian version of the TED conference. And we had scrambled to get this thing working at that time, and this was the live performance. So this is sped up. The performance took about 6 or 7 minutes. We got it down here to about a minute, so you can see what's going on. Finds all the pieces and has some, pretty straightforward motion planning. Grabs the back. I don't know if you noticed it, but one of the legs actually flew out. So threw it back in. So you got to improvise. It's funny when you see people clap at a robot. It's kind of an interesting thing. I mean, I mentioned this to people before and say, well, they're really clapping at you but that's not true. When we've had this on display, when people don't know that we're there, people clap after they see it do its performance. It's kind of a neat thing. So, as I said, this was a collaboration with Max Dean and Matt Donovan. What are some of the lessons learned in doing something like this? The first is that public has a very low failure tolerance. You know, we did this in front of hundreds of people. It was a big event. The organizers, you know, basically were saying this better work, otherwise this would be a complete disaster. You know, people pay money. They pay something like $5,000 to attend this 3-day conference. They want this thing to work, right? So it's a neat environment to be in. The stress the importance out of the box system, you know, you show up 3 hours before the event. You can't go there 3 days before the event and set up your system. You know, there's a lot of stuff happening. So you got to be able to show up, get your thing up and running, and to deal with circumstances that you couldn't anticipate ahead of time. So it really guides your thinking of how to design a system when you know that it has to be set up in no time, and if something goes wrong, you better be able to improvise. And the third thing I learned is that a bit of fear is not a bad thing. Too much fear can be debilitating, but a bit of fear is not a bad thing, right? Knowing ahead of time that we were going to do this live performance and that this thing better work was a very strong motivator to make sure that we didn't take any shortcuts and that we really had a robust system. So now I'm going to jump to this company, Kiva Systems, of which I'm a co-founder of. And some of you may know a little bit about it. I have this brief 30-second video. Gives you a very, very quick outline of what the company does. It's a logistics company. The idea is to move inventory in distribution facilities. So instead of having people walk around the warehouse, we have hundreds of mobile robots that pick up the inventory and they move it to the perimeter of the warehouse where people pick stuff off the shelves and they fill orders. The largest warehouse that we have is roughly 1,100 robots, between 1,000 and 1,100 robots. Yeah. So the key idea here, what was the motivator, is if you order something, say from Amazon, how are the which many of you probably do order books from Amazon, you know, how is it that the orders are filled? There's really two extremes. The first is workers move to locate and pick items. So you have a whole bunch of people walking around these warehouses with carts and they're filling orders. They have a list. They can be guided by voice. Okay, you have to go and pick up this order, etc. So that's one extreme. And the advantages of this extreme is that it's very flexible, easy to get up and running when it's people that are doing all the intelligent stuff. But it's not cost effective, so that's when people move to fixed structure automation, sorters, conveyors, and carousels. The problems with these types of systems, even though they can be cost effective in the medium to long term, is that they're relatively inflexible and they can take up to 2 or 3 years to set up. And in today's environment, it's very difficult to plan something 2 or 3 years in advance. So that was the motivator for the business model around Kiva System, to use these hundreds of mobile robots to move inventory. I'm not going to talk too much about Kiva, the problems. I've talked about it at ICRA conference before, and many of you people were there, but just to give you an idea of the complexity of doing something like this, you know, you got thousands of these robots, and we have to decide, you know, which of these robots goes and picks up which of the inventory, which station do we bring it to, where all the, you know, 20, 30, 40 people are filling pick orders. Once you've picked an order, where do you store it? Okay. How do you make sure that these robots don't collide? How do you make sure that you do proper battery management, et cetera? So there's a lot of decisions that have to be done in real time, in addition to being able to move inventory that can vary from 100 pounds to 1,000 pounds. And some of our bigger robots can carry 3,000 pounds. So there's a lot of interesting things. So what are the key idea here that we've employed in making our system is we try to do as much model-based as we can. So we have our system, and we have a model of our system. We monitor the outputs of our system and the outputs of what our model tells us our system should be. We notice discrepancies. That allows us to refine our model, and our control is parameterized by the parameters of our model so that we can continuously compensate for things that change over time. And this is one of the nice things that we'd like to be able to do, which we don't do right now, is right now this is a manual process. The design of the this happens in real time, but the design of the control system is done based on things that we do. It's done by people. But what if you could actually change the structure of your controller based on data alone from, say, observing tons of these warehouses operating? Could you actually automatically do design to take advantage of the things that you're learning from all of this data that's coming from all these different warehouses? And the other co-founders are Mick and Pete Werman. So what are some of the things that we've learned doing Kiva Systems? So one is the importance of architecture, hierarchical modular system. We tend to put a lot of emphasis in algorithms in an academic setting, but my experience has been that architecture is just as important, if not more important. How do you actually architect the system? And it's something that's really not taught, right? It's not something that you read papers on, and it's because a lot of it is design. And design is an art, and art is difficult to do research on, right? But doesn't mean that it's not important. Adaptation. One of the key reasons why we have a system that's commercially viable is that we do a lot of adaptation and learning. So we learn from our environment. We learn from operating the system. That allows us to make a system for a relatively not expensive amount and have the system tune itself by running. And one of the things that's really interesting is that control, in my mind, is the invisible magic to make stuff work. People only notice control when it doesn't work. When you see these robots doing all this great stuff, and they're not running into each other, they're carrying all of these loads, and they're doing it in such a way that makes it completely transparent to the user, most people just completely underestimate the complexity and the sophistication of the control behind it. So this is a very powerful tool. Control is a very powerful tool that can do great things. It's invisible. That's the downside. You don't get a lot of publicity for doing controls, but it's extremely powerful. This is a picture. The other lesson that I learned is startups is a lot of hard work. I think I'd have a hard time doing it. This was a picture taken at 3 in the morning when we were getting ready for some investors to come and kick the tires of our system. So we were staying up all night and doing it. I don't think I'd have the energy to do that anymore. So all of these things that we've learned from doing competitions, from doing these exhibitions, and from having done a startup, with now over 300 people, I kind of wanted to take all of those best practices and kind of insert them into my research program in Switzerland, where I moved there in 2007. So, some of the key requirements that I wanted to stress in my group, because I wanted systems to be robust, to work, and to be relevant is, well, first, this is an obvious one, build a world-class team. You want to have a great team of students. Simulation was not good enough for our research. We really need to work on physical systems. Physical systems keep you honest. Building hardware takes a lot of effort, but a lot of times, or most of the times, it gives you key insights that you just don't have alone if you work in a simulated environment or in a purely analytical environment. So that's a requirement for us. And these things that I talked about in the title, zero-downtime demos. This is a way in which I try to impose this robustness requirement. So as I said, if you come and visit our lab, you can come and see any of our experiments, and within 5 minutes, we can give you a demo of something working. Now, it may not be the latest thing that we're working on, but within 5 minutes, we want to be able to give you a demonstration, a compelling demonstration of any of our hardware test beds. And the other one is we like to do public performances. And I'm going to end the talk with the recent public performance that we did in France in front of hundreds of people involving flying vehicles. So let me tell you about some of the projects that we have going in Switzerland that have some of these key components. So the first is the balancing cube. This is a tall structure. It's actually over 2 meters tall once it's on corner. It has 6 modules on each of the face of the cube. And these modules are self-contained, but they're interconnected over a controlled area network bus, a CAN bus, so they can share information. And they can coordinate their action to stabilize the system. Here you see Sebastian pushing it. It's robust to some pushes. If you push it too hard, it will fall down. Okay, so what are some of the research that we're doing on the balancing cube? One of it is distributed and event-based state estimation. The idea is actually, I'm not going to get into algorithms, but I'm going to tell you the key idea behind one of the things that we're looking at, and it's the following. How do you limit the amount of information that you have to share in order to achieve this collective behavior that you want of the system being stabilized? So, and the idea here is to only send information if you have to. So how do you do that? So in each of these modules, we run two estimators. We run an estimator that has access to common information and local information. We also run an estimator that only has access to common information. When we see that there's a discrepancy between what the common estimator is seeing and what the local estimator is seeing that also has global information, that's our cue that, hey, everybody else has a misinterpretation of what's actually happening to us, so that's when we send information. Okay? So by doing that, you can greatly reduce the amount of communication required to achieve a certain objective. These are some of the experiments that we've done on the cube, where we show if you have full communication normalized to 1, you have a certain level of performance. Think of performance as how much you sway back and forth. And if you adopt this algorithm of only sending information when you have to, you can trade off communication for performance. So here the performance is not as good. It sways a little bit more, but your communication is greatly reduced. If you want better performance, then you can increase the communication, and you can do that by setting various thresholds. Just basically one parameter that tells you when should you send information and when should you not send information. Back to the thing about public performances. For this testbed, we've shown this in Italy, and actually we've shown this in Italy twice, once in Genoa and once in Milan. This was at the IFAC Control Conference in Milan this summer, where we had it on display for a day with various people coming to have a look at it. And this is Sebastian, the PhD student that's doing most of the algorithmic work on the system. Okay, here's another testbed that we have. It's called the Blind Juggler. And when you see this video, just keep in mind that there is no sensing of the ball. For all these things that you're going to see, the robot, which is basically just a paddle that goes up and down, does not know where the ball is. So there's, yeah. Okay, so we have a lot of other videos on the web if you want to have a look at it. Let me tell you about some of the research that we're doing with this testbed. This is what we call controlling the uncontrollable. And basically it's this paddle that has 4 surfaces on it, so we can juggle up to 4 balls at the same time. And the objective is going to be to take these identical systems, which are these different surfaces on the paddle, put 2 balls on it, and control it in such a way that we get to an arbitrary stable equilibrium of the system. And that may seem impossible to you. You have one control surface that you're actuating. The systems are identical, and if you apply any definition of controllability, any deterministic definition of controllability, it'll tell you that the system is uncontrollable. But in fact, it is controllable, as we are going to demonstrate with this video, and then I'm going to tell you a little bit about the theory behind it. So, initial condition, 2 balls resting on each of their respective surfaces. The goal is to get this equilibrium where you see the red and white ball are 180 degrees out of phase. Okay, so how do we do that? Okay, so we have microphones. So they're blind, but they're not deaf, the jugglers. They can sense when the ball's hit. And what we're going to do is switch to chaos. So the system exhibits chaotic behavior if the paddle is going at just the right frequency. And this is how we can break the symmetry of these systems doing exactly the same thing. And then, at the right time, we switch to the equilibrium solution for the paddle. And lo and behold, now we have this periodic motion that we wanted to get to, right? So let me kind of summarize again what we did here. You have a whole bunch of systems that have identical dynamics. That's basically this F is the same for all the I's, and they have the same control input, this 1U. So actuating the paddle is the 1U, and the fact that you have these balls on identical surfaces is the fact that you have identical dynamics. What you can do is you can exploit, for this particular system, the fact that it exhibits chaos when the paddle is moved in the right way. So you have, this is the strange attractor that corresponds to the dynamics of our system. And what you can then do is then construct experimentally and in simulation the regions of attraction of your stable orbits. And you can do various algorithms. What I showed you was the most straightforward one, which was using the microphone data, estimate the state of the system, and when they're in the right attractor, switch to the periodic motion, and that's what you saw when we switched from the chaos to the periodic motion. So we want to do that with multiple balls, and we want to do much better transitions. Right now we're just doing a switch from chaos to periodic motion. Can you do something in between to really make the transition as quick as possible? So it's an interesting study in dynamics. So we've demonstrated the juggler in its various forms in various venues all over the world. And it's actually in the private collection of the Paderborn Museum in Germany, where it's part of their exhibit on juggling machines of Claude Shannon. Claude Shannon was actually an avid juggler. He built a lot of juggling machines, and when they heard about this project, they commissioned us to make one of their a juggling machine for their exhibition, and it's been traveling on the road in many places. So again, it's this notion that we want to be able to design a system that can be in exhibition for 3 months. We've actually displayed it in near Naples. It's, there it is, Futuro Remoto in 2009. It was on loan there for 3 months, and it ran there without a problem. And this is Philip, the PhD student that's doing all the work on the Blind Juggler, all the algorithmic work. Okay, let me tell you a little bit about the flying machine arena that we have at ETH. And again, we have a lot of videos, but I'm just going to show you a little brief 30-second video of the various things that we can do in the flying machine arena. This is the typical control experiment of balancing a pole. This is playing ping pong. That's not really ping pong, but doing some flips. We do choreographed motion to music. So we do this in this very large space that we have at ETH, which is 10 meters by 10 meters by 10 meters. Here's the cube that you saw earlier, which is 2 meters tall. You know, it's 6.5 feet, so you can get a sense of how big this space is. And this is where we do all our flights. We have a motion capture system that allows us to see where the objects are, and we have various control algorithms that run on the vehicles and off of the vehicles to do the things that we showed you. And these are the PhD students that are doing work in this area. But what I want to show you now is this live exhibition that we did in France in December of 2011, just so a little while ago. It was at the FRAC Centre near Paris, where we built a 6-meter tall structure composed of 1,500 foam bricks using our flying machine, our flying vehicles. And this was done in front of a live crowd. So we had people with these vehicles flying overhead, definitely a lot of stress. And we did this successfully over a period of 3 days, and here's a very brief video showing you the process. There's much longer versions online if you want to have a look at it. These are the charging stations that the vehicles would autonomously land on. This is one of the flying vehicles with a camera on board. So this is about 20 feet high. This is a collaboration with Swiss architects, Matthias Kohler and Fabio Gramazio. So this was an installation which wasn't just about the robots building the tower. The tower had a very specific architectural context, and it was of a futuristic building, a small city in the outskirts of Paris on the main rail line, the TGV, where this would be 600 meters tall. Okay, so 60 stories, actually more than 60 stories. Each of these modules, these foam bricks, was supposed to represent a 3-story mini structure. So this is what the inside of the building would look like. Here you can see the modules and people living in the structure. And of course, you would never have people here while the thing would be put on, but this was added afterwards to demonstrate the concept. What's really interesting about this collaboration was that the constraints, so I met Fabio and Matthias, and we knew we wanted to work together. We decided to build this tower. The constraint of using our flying vehicles to build something actually motivated them to build the city. So it was an interesting collaboration. It's not that they had a vision of the city and then we decided to build it with our vehicles. It was through the collaboration of what can we actually build that they thought, well, with these vehicles we could build this. And what's interesting is that after they conceptualized this building, they built a small scale model. They did wind tunnel tests to show that it actually made a lot of sense. Structural stability is very high with this type of system. It's like a shell. So this is actually viable. Somebody someday may actually build a building like this. I don't know if it'll be done this way, but nonetheless. So some of the, again, I have a theme here of robustness, and I'm showing you, but I also want to give you some of the technical details of how we did this at the same time. The idea was quite simple. We had a blueprint, the specifications for how the building would be built, and this is what the interface, the API that we gave to the architects with tolerances. And then we had a program called the Foreman, which would read the blueprint, and it would communicate to the crew. The crew are the vehicles, the agents that are associated with the vehicles, and they would actually do the construction of the building. And there's a configuration file that they both read to make sure that everything was consistent. And these are the folks that were responsible, in addition to my PhD students working on the flying machine arena. These are the folks that worked on the flight assembled architecture. By the way, Kaysen did his undergraduate degree here. Some of you may actually know him. I think Bill does. He gave me a letter of reference for him. Yeah. Yes. Did a great job on the project. So to conclude, actually, this concludes my talk, and I'm hoping we have a lot of time for questions. So hopefully I showed you through the anecdotes and through my experiences of kind of what key ingredients were in order to build successful systems. And robustness is a big key here. Things have to work. And how do we incorporate that into a research environment in Switzerland? So the first, as I said, we need a world-class team. Outside of that, we want to work on physical systems. We have to have real hardware in our systems. And we like to do zero-downtime demos. Always be ready to give demos, no matter who shows up and how little time that happens. And it takes a lot of effort to do that, right? But once you have this in place, there's a lot of benefits, right? There's a lot of benefits simply because people come and see your lab and they're excited about what they're seeing. But the other one is that it's an investment, right? As soon as you have a system that operates in that way, even though it may take a year to set up, you can do, your research moves much, much quicker, right? Because everything is always working. Plus, you're teaching people skills that they're actually going to need if they're going to deploy real robotic systems. Because, as I said, you know, the fragility and the lack of robustness is really an Achilles heel in robotic systems. So it's a great skill that everybody learns. And it also makes you focus on the important algorithmic aspects that you may not know if you're not always pushing for, you know, immediate deployment of the system. You know, how reconfigurable is your algorithm? Is it easy to set up? Is it easy to change? These are important attributes that you don't consider if you're just writing papers without doing quick demos. And the third, of course, is the public performances, which is really the kind of corresponds to this. Not only do you want to do demos in your lab environment, but push yourself to do demos outside of your lab environment, and that opens up a whole bunch of problems, but really also pushes you to address things that are really key in making a robust system. So with that, I'll finish and happy to answer your questions.
Questions?
I have three. One is Kason working out really well. How's he doing?
So he has 6 job interviews, 6 offers, and we only hired Kason to work on this project. So he wasn't to be a PhD student. He had finished his master's, and it was like, you know, he wanted to live in Europe for a while, so perfect match of interests, and he did a great job.
The second question is, in your juggler, I can see how you control the vertical, but how come there's no, why doesn't it just kind of roll up? Or there's a little bit of...
There's a curvature equivalent of a 8-meter radius diameter sphere. And you can design it, you can prove that it's a stable passive system.
And then the last thing was, I loved all of the things you said. There was one thing that was, I thought, conspicuously absent, but I'm sure that's, and that is the design, test, redesign, test, get the thing.
Oh, yeah.
And so you got lucky on that one when back in '86, right?
Yes.
Didn't have a chance.
Yes. Yeah. So there we got lucky. Although I think we did a lot of the integration, sub-integration. Without the computer, right? So we tested the heck out of the mechanical part with the electrical part. I had tested my algorithms on my Timex Sinclair computer before, so all of that was tested, and then putting it together, that's why it went so well. But yeah, I completely agree. You know, I hope you didn't get the idea that you should only design something once perfectly and then it works, right? There's so many iterations that go on here. But the point is that just because you're iterating doesn't mean that you forget about what you just built. You know, keep it there, keep it working while you're working on something else. So you could be working on the next generation while still keeping the old version up and running so you can give demos with it, for example.
Great stuff. I have more questions, but I want other people to ask questions.
Other questions?
So how do you actually interleave that getting the system robust and doing research in reality? Because you cannot say that, okay, I'm going to first
Yep.
get the system robust and then I'll do research.
No,
You have
you're
to
right.
somehow interleave that.
You're absolutely right, and I think you said it. It's interleaving it, right? It's a process, right? You build something, you have some ideas that you want to explore. You build it, sequence of prototypes, and then you do. As soon as you get something that you can do some interesting research on, you do it. You publish some papers. You realize, oh, there's more I want to do, and then you kind of leapfrog it from there. It's not a process of you go off and build a hardware test bed and then you start doing, no, you certainly don't want to do that, right? Because we do have constraints. We're in an academic environment. We have to publish. We have to, the students, how are they going to be gauged when they're done? It's not going to be on the videos. It's going to be on the papers that they write, right? So, but at the same time, they do have to learn these skills. So yeah, it's a process. It's an interleaving. It's a good way to put it.
Can I ask a question about the wireless communication?
Yeah.
I assume that you have used the Kiva Systems and Blind machines for communicating each other to
Yep.
use the wireless communication. Do
Yeah.
you have any put any efforts on making it more reliable?
So with Kiva, it's easy. So the I got to be careful how much I say, especially if I'm on videotape. But the idea is quite simple. Just you make your protocols and your architecture such that they're robust to arbitrary failures in wireless. So you want to be, you want wireless degradation to affect your performance, not your stability. That's really the key. Okay, so obviously if wireless went down, we wouldn't be able to operate our warehouse. But it does it in a degraded way, right? It's if you have wireless problems, the system still runs, but you still have stability. So that's really the key. Architect your system such that you are robust to wireless, because wireless failures will occur. Now, our flying machine arena, it's not. It's not robust to wireless. We're getting there. We're getting better and better at making it more and more robust to wireless, by putting better algorithms on board, more local awareness. But it's, when we did this demonstration in France, we were definitely, a little bit crossing our fingers. I don't think there's no way we could have done this in the United States, having vehicles flying around over people's heads. France, yeah, go ahead.
Yeah.
I was wondering about the difference between architecting a system for your students to build versus your company to build. Did you have any ways you parse out jobs differently or approach the complexity of the system?
Yeah, so I mean, one is what a company can do is much more than than you can do in a research environment. Although when you're starting a company, it's a startup, you really are just scraping things together. So. I think part of it is that in a research environment, a university environment, part of it is education, right? So you have to consider the fact that you're bringing people up in their skill level, where in a company, it's not like that. In a company, you hire the best people that have a lot of experience and just to get the stuff done. So, I mean, I think that's one obvious difference. I think always keep in the back of your mind that in a research environment, in a university environment, our key product is you guys, educating you guys, and that always has to be at the forefront.
So before I abandoned my boss used to say, an A team with a B plan is far better than a B team with an A plan. In an academic setting, how do you build a team?
So the first is, you have to be fortunate enough to be at a place where you can attract great students, and you guys are. So you certainly have that under your belt. The second, of course, is you work your way up there. I remember when I was starting as an assistant professor at Cornell. We had some people that were interviewing, and they would tell me, "Oh, I got accepted at Caltech with your advisor, actually. Should I come here or should I go there?" And I would just tell them, I'd say, if I were you, I'd go there. Not because, well, I'm being perfectly honest with them, right? I'd say, I'd go there because they have all of this in place, and I just don't have that here yet. I'm not going to lie to the guy, right? So it takes time, right? It takes time. You work your way up. At some point, I had students telling me that, should I go there or should I go here? And I'd say, no, you need to come here, and here's why, right? But it took me years to get to that level. So you have to build up. You have to build up your credibility, everything else. So I think that I don't think there's a simple thing. I think you start with, you do some things, you do them well, you get attention, you can point to your success stories, and then you build from there. I mean, it's taken a long time to get here. It wasn't something that I did in 1 or 2 years. Yeah.
So I was wondering if simplicity trades off with robustness. Like, for example, you have this wheeled robots playing soccer, and if I give you a humanoid robot, do you think you get the same robustness with that complicated system?
Yeah, so maybe that's why I never do the complicated stuff. I only do easy stuff, right? Yeah, look, I mean, there's some things that are inherently more difficult to even just do basic things. Walking is a good example of it. I mean, now I think it's progressed enough now that you can buy some, pretty good platforms that will do some nice walking, but that's only pretty recent. That's just a very, very difficult problem. I think it's just time. I mean, RoboCup, if you looked at the performance in 97 and 98, it was also really, really crappy, and it got better over the years. But it is a much easier problem. Robustness with walking machines, I still think it's a viable, this philosophy of robustness and demos, I think is a good one, because then it forces you to think of, what are simple mechanical designs that you can exploit? You know, like people that exploit passive dynamics in walking, I think it's a big plus, right? Because it's, you know, of course you have to build on top of that, but I think this notion of forcing yourself to have robust platforms, even though for something complicated like locomotion, I still think is a viable, it's a viable model. Yeah. Yeah.
Do you buy your hardware as a prodigy, or do you design all of them?
So we try to buy stuff if we can. We only design and build stuff if we have to. It turns out that for a lot of things we do, like the balancing cube obviously is completely custom made. The Blind Juggler is obviously custom made. Our flying vehicles, we buy the frames, we buy the motors, we buy the motor controllers, but we do all our own electronics because we like to have control of what's going on. You know, Kiva as a company, we design and build everything. Yeah, if you can buy something, why not? Bruno.
So how do you design robustness? What are the things?
Dan Kodacek asked me the exact same thing when I gave a talk at Penn, and I don't know. I think it's I can't give you a recipe. I think I think design in large part is art. It comes from practice, and there's a whole bunch of rules of thumbs that I have that I follow, and there's always exceptions to them, and it's not clean. It's not. I think that's why it's so hard in an academic setting to have you know, hardcore design as a you know, to hire a professor of design. I think some universities are farsighted enough to know that that's fine, that you can't put design in the same category. That has to be treated differently as developing algorithms. It's less tangible. So I just have a lot of rules of thumb and things that I follow, and you know, controls is like that too. You know, if you do control design, you know that there's separation of time scales that you do. There's various tricks and things that you learn you can't just read in a textbook. You have to just do it. So that's why it's the other important of actually doing stuff. So I'm sorry it's not a very satisfying answer, but.
I'm satisfied. Put your rule of thumbs in an email and send them.
Okay, one final question.
What's been your biggest failure and when did it happen?
My biggest failure and when did it happen? Sorry?
And
Why did it happen? It's hard to say the biggest, but I know one big disappointment we had was RoboCup in 2001, where we had a really great team, great robots, and we lost in the semifinals. And the reason we lost in the semifinals was that we were so concerned. We had won 2 years before then. We were so concerned with having a team that was. The way I like to put it is we try to play like Brazil. You know, we wanted to be this really beautiful team that did all this great stuff, and we kind of lost track of the things that you needed to do to win, and that was disappointing because of the team that you have, right? You have these, you know, I could compete again next year, but these students, for them, it was the only time they could compete, and it was just to see their faces, to know that they had this great team, and you know, and the fact that they went home without winning the first place was very disappointing to me and for them. But you know, you know what that's like. Sometimes you have a great team and you don't win. Sometimes you have a so-so team and you end up winning. So that's all competitions are like that.
Okay, let's thank for